Welcome to Hot Chips 30. Session 2, Graphics Solutions.
First presenter is Srinivas Chennupaty. Srinivas is an Intel veteran with demonstrated acumen in CPU, GPU, and SoC architecture. Throughout his career, he has a long history of innovating microarchitectures, instruction sets, and SoC development. He's worked on SSE for many generations and has also introduced AES-NI. He's also worked on big caches, embedded DRAM, and he's also worked on shared virtual memory subsystems. He's the lead architect for Intel's latest generation of big graphics products, where he pioneered the usage of large caches. And he's the chief architect of the -G line, or the G series, of products, which was just introduced at CES this year. Please welcome Srinivas.
Thank you, Ralph. I'm usually fairly loud, and now I'm amplified, so I'll need to sort of back off a little bit. So thank you all very much. It's my privilege to represent Intel here to talk about what must definitely be one of the most fun and unique products that I've worked on in my career at Intel. The usual notice and disclaimers. I can't read it from here. Hopefully, you can. So, see, it's 2018. Over 3 years ago, there was a problem statement that was put to me, which is the business unit wanted to figure out how to combine the goodness of gaming in a thin and light form factor. So at that point, and even to a large extent today, you have usually the choice of a professional laptop, which is thin and light with integrated graphics, with battery life, a good display, but somewhat not so high resolution gaming, simply because it has to be in the constrained form factor. And then you have laptops which range from the slightly thick to the barely transportable range, which have big graphics and a lot of memory and very little battery life. So the question was, can we bridge the divide between these two across a generation of products, across several generations of products, to be able to deliver gaming capabilities while not giving up the thin and light attributes that make modern laptops so desirable. And and this is rare, where I was basically said, there were no constraints. Do what you have to, and go pick whatever IP or SoC solution that you had to. So the result of that was something which we introduced earlier this year at CES. It's got a fairly long name with many syllables to it. Internally, we call it something Kaby Lake-G. It is effectively using 3 components, and the rest of this talk, unlike the other talks in this Hot Chips conference, is more about how you use multiple chips to create an innovative product. And the components in this are the Kaby Lake family of products, which is Intel's mobile form factor, and they range from fanless all the way to high-end 65-watt and above laptops. And then they're coupled with an AMD Radeon RX Vega M. And this is part of the fun of working in this project. When I talked to several folks inside the company, they just wouldn't believe me. I said, this is what we're working with. No, you're kidding me. And somewhere inside Intel, we actually have a framed version of the original agreement that we and AMD signed. So that was fairly unique, I think, in my history, and I think for anybody else too. And then we had the Radeon RX part, which was customized to our needs. And one of the goals that we wanted to achieve at that point in time was to enable virtual reality in a mobile form factor. Again, this was when we started out in late 2015. One of the other innovations which we want to do is stay in a mobile form factor, and staying in a mobile form factor sort of precluded the use of GDDR. Staying on a single package precluded the use of GDDR because the package would simply be too ginormous. So we turned to a solution with HBM, and this was at that point in time, this was planned to be the first high-volume mobile part with HBM memory, which delivers high bandwidth. It's still a relatively low power, both at dynamic and also at the standby. So this is getting into a little bit of detail. Most of these should be familiar to you folks, but one of the highlights is this. One of the standard attributes is, as best as I know, this particular subsystem has the largest number of displays that ever pinned out. We have 9 displays, and there's one form factor which in Intel we call NUC, Next Unit of Computing, which actually pins all of these displays out. And it also includes all of the capable integrated graphics and the media transcoding capabilities that come with the part, but it also allows you to selectively switch on the discrete graphics capabilities when you on a user selected mode, or also by heuristics when the demand on graphics is high. So what I want to walk you through is some of the logistics, technical and otherwise, which we went through in making this happen. So there were 2 critical enabling Intel technologies which coincidentally happened to be developed independent of this, but were critical in delivering the solution. One of them was something we called EMIB, or Embedded Multi-Die Interconnect, and the second one was extending our dynamic platform thermal capabilities to include separate SoC into the mix. Now, many of you are familiar with all of the packaging technologies that we have, and so just to a little bit of background and to provide a little bit of contrast, today you have, if you're connecting multiple chips onto an SoC, right, in a planar form, let's say an Intel CPU or an Intel PCH, you clearly can connect the low density interconnect, through connections on the package. And then in the industry, prior to Intel's innovation, there's also a solution for connecting high density interconnect. For example, HBM has a very high density of interconnect, which is not sufficient to route through the usual packaging rules. So the solution that the industry has adopted is basically create an interposer, which is effectively another piece of packaging, and then route the high density connections, and then make the rest of them as vias down to the regular packaging material. Now, the critical portion of Intel's innovation has been to realize that there is a way to limit the amount of area in the package that is required for high density interconnect and embed it in a regular package. What this allows you to do is sort of have your cake and eat it too, where for the bulk of the interconnect that does not require the high density, you use the regular packaging, and then there's a little bridge that's built into the package where you have the specific areas between the dies on both sides, where the high density interconnect, for example, HBM, it doesn't have to be HBM, it could be any high density short run interconnect, can be routed through in a passive manner. And what it allows is, clearly there's a bunch of usages, but what it allows you to have a large number of wires and a large number of data at a very low power envelope between 2 dies which are physically adjacent to each other on a package. Now, there's one application with KBLHG. There are other applications that are already out there as Intel products. One of them is a Stratix FPGA, which connects to HBM in a similar manner. And what EMIB allows, or at least the promise of EMIB, is allow you to span different manufacturers, different process geometries, different vendors, and build a product in a TTM manner and deliver goodness in far less than the amount of time that it takes for a usual SoC, at least a commercial SoC development, unlike the super fast Broom chip that we just heard of. So some of the other challenges that we had, right, other than working with the manufacturing folks of two companies, was one of the constraints that we had was we could use any SoCs, but we could not drive changes into any of the SoCs. So we had to take off-the-shelf components, from both sides, or at least drive minimal changes. So one of the original challenges was the connection between the SoC, the CPU, and the graphics was PCI Express. And that is PCI Express in a discrete form. Now, usually that PCI Express connection is designed for a routing length of 8 inches, through the package, discontinuity on the motherboard, and then through the connector. And it's usually AC coupled. So we did a lot of simulation, but we always had our fingers crossed whether those simulations would work when the run is literally 2 inches. And then Z height challenges. It's a mobile form factor. One of the attributes of a mobile form factor is that for heatsink reasons, the heights of all the components have to be relatively close so that the heatsink can contact all the components. Now, in our case, the HBM was actually at 700 microns, was actually taller than the other two components. So we had to custom thin the HBM die, and that's always a fraught process because it's custom, and sometimes if the thinning process goes awry, then you adversely affect the attributes of the HBM itself. And then the entire process of bringing the two parts together required manufacturing and testing independently on each side, and then packaging in let's call it a neutral territory, and then testing individually on both the CPU side and on the GPU side to make sure that all the components are functioning properly. And then you multiply this by the number of geographies where the assembly, manufacturing, packaging tests happens. It's a fairly logistical nightmare. And then the last part is for development, and then developing common engineering and production test flows for high volume manufacturing, and then customer interface. These were all challenges that we had to work through in order to put the product out in a short period of time while still protecting the relative IPs from either sides. So the second one which allowed us to basically bring the part together was what we call dynamic platform thermal framework. So Intel has a long history of platform power management, starting from the days of, I call it Broadwell, I think it's the 5th generation Intel, and even before that, where we take a holistic view of all of the components in the platform in order to manage the static and dynamic power for each one of them in order to maximize battery life without compromising performance. And one of the factors there is Intel CPUs have a very wide frequency range, dynamic frequency range with various flavors of turbo. And the name of the game here is in a mobile form factor is to maximize the performance that the user sees while minimizing the thermal impact that the user may come into, while adapting the CPU and all the component frequencies to the workload mix to maximize the performance to the user. The other factors which typically affect mobile performance, especially as you go into the higher power envelopes, are whether the AC power availability AC power is available or not, the skin temperature needs, and then also a whole range of OEM tunings which allows you to customize the platform and provide differentiation from vendor to vendor. So this is a picture of how, of products before KB Lake G, where everything from the fan control, from the SoC temperature, SoC power, from the platform component hub, from the SATA frequency and the SATA power, from the external interfaces, everything is controlled to minimize the power when it's not needed and maximize the power where it is needed in order to ensure that the performance stays at the peak that it can, subject to the thermal constraint at all points in time. So, active skin temperature management. Now, you guys have all run benchmarks many times, and you know that there is a difference when, especially in fanless, we call it fanless, other people call it mobile, but in fanless form factors where depending on the temperature, it's a cold start or it's a warm start, you have additional thermal headroom to take advantage of. And this allows you to get more performance when there's more thermal headroom. Now, think of harvesting this thermal headroom on a continuous basis in response to the workload characteristics. By workload characteristics, I mean whether it is CPU bound, whether it is GPU bound, whether it's memory bound, whether it's I/O bound. And I/O could be, storage or even Wi-Fi or network. And then ensuring that the CPU frequency is throttled back if you don't need that performance. And similarly for all the components in the platform level, not just at the SoC level. This allows you to get significant performance upside when you have thermal headroom, and in some cases, it allows you to sort of throttle back components which are not essential to the performance. If I'm playing a game, perhaps I can throttle back on the I/O speed subsystem and give you significant upsides versus not having DPTF active. So DPTF with discrete graphics. So what KB Lake G basically did is add the discrete graphics component right into the mix and allowed it, and I have a foil coming up, and allowed it to play in the same form factor as a participant in the mix. And what this allows us is basically multiple vendors like to customize their hardware to their own specifications. So we provide hooks in the form of power budgets that each SoC component can manage to or is programmed to, and power policies that each OEM wants to implement and can then use the control mechanisms present in the platform to modulate power, temperature, and fan speed. Power sharing control. So the whole concept here is, since, as I mentioned, these were two components coming together which did not have any shared interfaces other than PCI Express, no sideband interfaces to control power. So we implemented a software power management solution. And one of the nice things is the thermal time constant is in the seconds. So we have time even in a software loop to manage this. So we have a power budget that we establish based on a heuristic that is under automated software control or can have user input, which establishes a power envelope for each one of the entities on a fine-grained time interval, and then evaluates the power consumption, the workload utilization, any target frame rate that is set, and then adjusts the power allocation in the software loop. And the power allocation, in turn, is managed to by automated hardware mechanisms on each one of the SoCs. So bringing it together, what this allowed us to do is essentially take the three components that you have of graphics memory, the SoC, and a discrete graphics chip into a form factor which allows the vendors to physically create either thinner form factors or more performant form factors compared to a solution where you had the discrete graphics on the motherboard. And as you can see, the Intel EMIB technology allows us to place, significant, in this case, 4 gigabytes of graphics memory on the package in a form factor which is mobile friendly. So as we say, proof is in the pudding, right? So on the left is an exemplary, there are no code names on that, right? There's an exemplary solution of what a Intel SoC, which is on the right, and then a graphics SoC with a GDDR of, I think it's GDDR5, and what the motherboard actually looks like, and then all of those components and how they look like in the KB Lake G form factor. And if I remember correctly, it's funny that we measure area in millimeters squared, but that's precious real estate in a notebook form factor. It's almost 3 square inches of motherboard area that we were saved. What this allows an OEM to do is add more components, perhaps another Thunderbolt a bridge, Thunderbolt to a Type-C bridge, or it allows them to basically shrink the form factor and either reduce in X, Y, or Z. Typically, when you take a 45-watt SoC and a 65-watt or 55-watt GPU, and an OEM designs them, they typically allocate the power budget in a fixed form factor because they don't know how each one of them will dynamically go up and down in power. They typically give a power budget to the SoC and give a power budget to the GPU. What this effectively results is in time periods where the GPU actually has power budget to give, well, the CPU can't use, and in times where the CPU actually has power budget to give, in other words, it is not utilizing the full spectrum of power that it can use, there's no way for the OEM or even for the system design to actually transfer to the GPU. Now, in Intel-only SoCs, we address this by, we have a solution called the fully integrated voltage regulator, where think of it as it's a bucket of power, and it either sloshes to the GPU, integrated GPU, or it sloshes to the cores, and it happens in, in hardware loops, in fine-grained time intervals, all on the SoC. But in the case of a discrete GPU, we can't quite do that because we don't have the budget. However, when you bring it together in the form factor of a package, we can still control not as fine-grained as we do on the SoC, but still much better than we can do in a discrete space. We can implement a similar power sharing. What this allows you to do is get more headroom and higher power budget and higher frequency for each one of the components, and results in either higher performance or lower power. And it's up to the OEM or the vendor to determine how they want to harvest those capabilities. And of course, the dynamic power sharing basically says that I don't have to design the cooling for a 65-watt GPU and a 45-watt SoC. I can design to, let's say, a 70 or 75-watt form factor, and I will let the hardware power sharing in there manage the power to fit in there, and I'll save on, again, Z height, because the cooling solution doesn't have to be as much copper, or in the number of fans I have to have in the system. And these are the usual benchmarks. These were compared to the competition at the point in time, and what it allows you to show is in the same form factor, we were able to bring together a solution which was competitive with the competition at that point in time, and actually delivered that performance in a noticeably better form factor. And by better form factor, it's, as I said, it's in smaller XY or smaller Z, or in more battery life, because you can use the extra space that is created in the motherboard by stuffing extra battery in there. It's really an OEM choice. So increasingly in the future, as we get to heterogeneous architectures and heterogeneous solutions, packaging is a critical tool in the arsenal of the SoC designer and vendor, and it allows us, at least what I have discovered, it allows us to be more creative in the choice of components that you can use, and be dramatically faster in a TTM time to market window. The entire Kaby Lake G product, from the time we actually made a decision, and in large companies, decision making is not the fastest. From the time we actually made a decision to go to the time we had a product, it was effectively 4.5 quarters. And we were able to bring this part on the very first silicon. Granted, these were SoCs which had already seen silicon before. On the very first boot up on what we'd call the A0, we were within 90% of our production performance on most of the benchmarks that we had set a target to. And a little bit of a shameless plug, but EMIB is a very cool technology which allows us to basically connect high-density interconnect and provide a path to be able to deliver higher bandwidth or more wires while not adding an entire level of interposer or packaging or cost to the platform. And then finally, when you're building complex systems, platform-level power management is critical in order to make sure that you can manage the power, and it's also more critical in order to deliver the performance that the end user requires while still managing the power budgets of very power-hungry SoCs. That's what I wanted to convey to you guys. I'd be happy to take a few questions.
Thank you, Srinivas. Great talk. Nathan, go ahead.
Nathan Brookwood, Insight 64. Congratulations on being able to bridge these two traditionally rival companies into one product. Maybe we can send you off to work on Middle East peace next. but seriously, in one of your slides where you show all of this in the single picture, you have EMIB for connecting the HBM to the GPU, to the Vega, but you don't highlight EMIB to connect the Intel SoC to the rest of the...
So, good.
Is that a mistake in the graphics, or am I...
No, it's a good question. If you think about PCI Express, right, it's differential signaling we routed off the package today. You don't need the density that HBM requires, so we didn't actually need EMIB. Now, EMIB is all great, but it does as packaging. You didn't need EMIB for the signaling speed and the density of the wires that the PCI Express connection to the GPU required. What you did need it, because HBM is like a 1024-bit interface, you need that to not overwhelm the shoreline between the GPU and the HBM. So you did not need it for the SoC to GPU, but you needed it for the GPU to HBM.
Okay, thank you.
Charlie, go ahead.
Hi, Charlie Demergent, Semi-Accurate. This has been built, or the GPU on it has been built as an AMD semi-custom project. What did you customize?
So one of the things we had to customize is the number of render backends. And the second thing we had to customize is that it was a derivative of an AMD product which had used HBM via the interposer technology, and the bump pitch between how the HBM interfaced with that interposer did not work with what we needed for EMIB, so we had to change the bump geometry.
Thank you.
Go ahead.
Jeff Smith from Citadel. Question about one of your last slides. You said that EMIB was a technology for bridging heterogeneous platforms or technologies or whatever. In both of the things you presented earlier, it was used just to bridge an HBM channel and not, per se, an SoC and an accelerator or any sort of third-party technology. What really is the plan longer term that you're allowed to say as far as talking between an Intel SoC and an actual third-party accelerator directly with EMIB?
It's a good question, right? One of the things that we must have when you want to create an ecosystem is standard interfaces. Now, EMIB is just a technology, right? It's a bunch of wires which go a distance. So the real question is, if you want to create a standardized ecosystem, you need an interface. Is it a single-ended interface? Is it a SerDes, right? So those are things that Intel is actually actively working on. And there was an announcement, I think, a couple of weeks ago on DARPA OpenChip. So we're trying to basically bring this to the market, but establishing an ecosystem is like requires a village. It can't be one vendor. So what we have tried to show is what the technology that exists and the potential that's there, but it hopefully requires more players to recognize the value of what can jointly be built.
So could something like EMIB or even UltraPath become more of an open consortium standard like PCIe, or is that presumed longer-term closed platform?
So when you say consortium, that almost already has a negative connotation with it. But I think the point is that it is a technology, and clearly you cannot build an open ecosystem where the technology is changing rapidly. And on the other hand, you don't want to create something and then never improve it. So I would imagine that there'd be something where there's improvement over time, but there's enough stability for multiple vendors to achieve ROI. It sounds like a fairly fuzzy answer, but that's as best as I can give.
Thank you.
Maybe I've got a question, Srinivas, if you don't mind.
Yeah.
So you've learned a lot about integrating different components. Now, any more insights in terms of what you would integrate on the same die versus what you put on a separate die?
So I think it's a good question. I think it's primarily related to how many wires are you pulling out, right? The pitch for any interconnect, when you I have a simple theory. When you touch data, each time you touch it, the longer you touch it, the more power it costs. So if you have ultra high bandwidth, right, you want to stay on chip. If you have, really low, but it has to go long, you go off chip. EMIB has a happy interface where the ROI of taking it off chip is still worth it, rather than the ability of having, or the need to taking, a very large SoC, another large SoC, and building them together, right? And it also allows what I call late binding, right? You don't have to design everything when you start. You can attach other things which talk the same language even later. That, again, goes back and requires that common interface.
Well, thank you very much, Srinivas. Thank you for coming over here.
Thank you,
Great talk.
folks.
Great talk. Lots of interest. Great talk. Next up is a talk from AMD. Talk is titled Delivering a New Level of Visual Performance in an SoC, the AMD Raven Ridge APU. I'd like to introduce Dan Bouvier. He's a corporate vice president and chief architect for AMD's client products. In his role, he leads the architectural definition for AMD's Ryzen family of notebook and desktop products. Dan has been in the industry for over 30 years with a focus on high-performance SoC architecture, microprocessors, and a variety of computing and embedded systems. Prior to joining AMD in 2009, Dan worked at Applied Micro, where he was the processor CTO in charge of the PowerPC product line. Before Applied Micro, he was the director of advanced processor architecture at PowerPC at Freescale and Motorola. And he also held various positions at Ross Technologies, Dell Computers, and Bell Northern Research. Dan received his BSE from Arizona State in 1986, and he holds 20 US patents. Please welcome Dan.
Thank you. Pleasure to be here. Wow, it's loud. To present this device. So Raven Ridge is our APU, the latest generation that we have in market. It's known in market as Ryzen with integrated Vega graphics. And so I'm going to go into this in more detail today. When we set out to do Raven Ridge, we had aspirations of really kicking the bar up in performance. We had done multiple generations of APUs at that point, and we were not really realizing the full potential of the fully integrated SoC at that point. And really around GPU especially, we had been integrating and restricted to smaller GPUs and very much limited by certain aspects that I'll talk about through the presentation. So while we were getting generational uplifts in performance, the customer, the end user, wasn't really realizing or visualizing an increased performance. We'd see benchmark increases, but they wouldn't really realize it. So as we set out, I think we did achieve our goals here, and I'll prefetch the end here with some performance. So this device is an SoC used in notebooks and desktops. It's actually been in market. It'll be coming up on a 1 year anniversary here toward the end of September. It does integrate our Zen microprocessor core complex with a high-performance Vega graphics engine, and then we also, as you can see here, focus quite a bit on power and power efficiency. And so some of the challenges we had up front was GPUs tend to have a very, very big appetite for memory bandwidth. So in a UMA-based system, getting the most efficiency out of the memory system is very important. The second area that's really important is managing power and how you efficiently move power in the chip. So I'll describe more on that. And then last but not least, because we are putting this in notebooks, battery life is also a key consideration. So first, I'll give a little tour of the SoC, just so everybody's grounded on what we have on it. So we start out with a quad-core Zen CPU complex. Each one of those cores is capable of 2 threads, SMT. We talked about this processor in the 2016 hot chips. So actually, to get the full breadth of this, you'll have to go back 2 generations or 2 hot chips, and hopefully everybody's paying attention. So we coupled that with a Vega graphics that we talked about last year, and so we integrated a smaller variant of that graphics engine. Then we also put quite a bit of new IP. This is, it's unique in a career to be able to go do a full-up, ground-up, almost clean piece of paper, and this device actually was, almost everything was new in it. So we put a brand new display engine, we put new video codec engines, we put a new audio coprocessor, we also integrated a new I/O subsystem, and in this case, integrated USB 3.1 with some USB-C native connectivity in the device. We also have a sensor hub on this that's always on, and that uses an ARM M4 core in that subsystem. So let's talk about some of the specifics of what's inside. And so I show a floor plan here, and you can probably make out on the left side of the diagram is the CPU core complex. On the right side is the GPU. We went big on this GPU. We actually spent more silicon area, I believe, if I remember right, and that GPU than we did in the CPU, even though we did a significant generational increase. This is 5 billion transistors in GlobalFoundries 14 SOI. I'm sorry, FinFET, and it's about 210 square millimeters. So despite the additional transistors generationally, we had about 60% from our previous generation Bristol Ridge device. The die actually, because of the shrink to 14 nanometer from 28 nanometer, ended up being 16% smaller, which helped us a lot in packaging, but did present some challenging floor plan issues. This sits on a BGA package and also as shown there, and it's also available in our micro PGA that's used in desktop sockets. So it's available in both places. So let's drop down through what's in the, and I'll start with the graphics since this is about visual. The Vega engine has 11 compute units, and this time we went to a slightly bigger cache. This has a dedicated L2 cache for texture caching as well as compute jobs. It has a very flexible geometry engine that was part of the Vega architecture, and then it has 16 pixel units. It has 2 render backends and an upgraded render backend in this generation. So this can do 12 million textures, per triangles per second. Sorry, at 1.2 gigahertz, which is our max frequency of the graphics engine in this generation. On the CPU side, again, we talked about this last year or 2 years ago. The Zen core complex has four Zens. When we did this engine, one of the key considerations in going to an improvement in the CPU side was that also helps visual. It not only keeps up with frame rates better in doing the CPU portion of the compute, but it also reduces power because it's getting done sooner and gets out of the way so that we have more power to dedicate to the graphics and memory subsystem. So in this case, 4 cores, each with 512K L2s, and then we have a smaller L3 cache in this version than we have in our performance desktop version. This is a 4 meg shared L3. One of the areas we focused on that we did a slight upgrade in this generation was in our boost algorithms. Again, we had very coarse boost stages in our previous generation processors, and so what we did here was a second generation of our precision boost algorithm. And what this does is it watches what's going on in each core, it watches what's going on in the overall thermal envelope, what's going on across the cores, and then it dynamically adjusts the frequency of each core. And can therefore get a much smoother performance curve depending on the current situation with the workload. And so this allows a much higher performance overall when you start averaging out across multi-threaded workloads. And we do that in 25 megahertz increments. When we put that together with graphics, now we start talking about how are we managing the thermals and the power and getting power to where the power is needed. One observation we had after we looked at a lot of graphics workloads is that they tend to run through phases where you have maybe a compute phase, and then you might have a render type phase. And this can even extend in some workloads to quite extensive periods of time, here showing multiple seconds where the CPU is very active and then GPU is active. And so what we put in this is the ability to dynamically move power back and forth, not necessarily a new concept, but we went like a step further in this generation, and that is we have on-die regulation that I'll talk about later that helps us to have a tighter control over that, so down to very small periods of time where we can be moving that power back and forth. And so shown here, as you can see, the graphics phase of a Firestrike workload spends a period of time in the graphics engine, and then it shifts to the CPU. And so we're able to exploit the full potential of the power envelope and power supplies during that. So at the heart of the chip is our fabric, and we've talked a bit about this in the industry. This is our Infinity fabric. So one of the things that goes into that and around that is the need for being able to move traffic to the memory system and back and forth between GPU and so on. So at the heart of this, really we can use this to drive CPU threads feeding the GPU resources, and in the CPU submitting tasks for the graphics rendering or compute. And then the other nice thing here is that we wanted to have one coherent control, one coherency across the SoC, so not just relegated to the CPUs only, but between GPU and CPU. And then also at the heart of this fabric is the overall power budgeting and power management of the device, and in a microcontrol subsystem that we have. And so what this does is it allows us in this generation to do more enhanced flow management and power management, powering on and off GPU or CPU depending on what's going on. And I'll talk more about that later in the presentation. So one of our big challenges we had early on is, and this is 2013, 2014 timeframe, is we knew we were going to do a major reset to the AMD product portfolio, graphics, server, and APUs. And so doing that, we wanted to come together with limited resources and put a portfolio together and turn that to market very quickly. So at the heart of that, we did define the Infinity fabric to go from very large devices, server class processors that we have in EPYC, to high-end graphics like we have in the higher-end Vega devices, and then into smaller mobile or mainstream desktop processors like we have in Raven. And so at the heart of this is the Infinity fabric and is a transport layer that we have, and at the edges of this is a scalable data port. This is common and has been defined so that we have very quick turn in terms of design verification and so on as the chip was put together. And we were basically building all of these chips that we've announced now over the past 2 years simultaneously in AMD. A big challenge, as you can imagine. At the heart from the coherency protocol is a version of hypertransport that we've had in market. So we had a lot of history with that. It was well proven coherency protocol, and so that was the underlying root of the coherence. The nice thing here is the scalable data port hides the complexities of the coherence protocol, so it's very much distributed. The GPU, CPU, and then the central point of coherency becomes the memory controllers, and I'll show more on the next slide. So this is a picture of Raven Ridge specific fabric, and so you can see in the center is the transport layer switches. These are crossbars, and in this case we have 4 of them. On the one side you can see the memory controllers, and those are the coherent slaves. And then across the top, you can see the CPU, and then you can also see that we doubled down on the GPU with a lot more bandwidth and extra ports, an extra port there. So those are coherent ports. And then throughout the rest, we have our multimedia, our display, and so on. Now, one thing to note here is I'm showing two regions, and that was because when we floor planned and we did the architecture of the device, we wanted to make sure that when we're in a very low power situation, like a display refresh, that we could have enough, we could shut off portions of the chip. So this is showing region A, region B. Well, in this case, when we're doing a display refresh or a video playback, we turn off the CPUs, the GPU, we turn off that portion of the fabric, that whole side of the chip shuts down, and we save the power. QoS is also super important, and here I talk a little bit about what we've done in the device. So we have transport request queues at each point of entry into the fabric, and in there we have 3 request classes. So we have a hard real-time, which would be useful for high bandwidth devices like display that do have a very precise need for bandwidth. We also use this for our low bandwidth things like audio, but to make sure that we don't get any any glitches in audio. Then we have soft real time, and this is used for video playback, like our video codec engine, where we want to make sure that we're keeping up with data movement. And then we have non-real time, which is essentially CPU, GPU, and so on, where the real-time situation is not as critical. Within this, the architectural, we have multiple virtual queues and virtual channels, and then we have priority classes. And so in this priority is managed end-to-end, so we can do escalation per virtual channel through the fabric. So, as I mentioned earlier, memory boundedness is a big problem for graphics, and so we had to take multiple actions to get the effective bandwidth up in this generation. Our memory subsystem can peak out at 50 gigabytes per second, and of course we have to manage that to the power budget available, and so having good efficiency is important. So starting with the CPU, having an L3 cache of 4 megabytes was nice. We didn't have an L3 in our previous generation, so that took some pressure off the memory system. Also going to the bigger GPU cache helped as well. This GPU has deferred primitive batch binning in it. That makes graphics traffic smooth out, and it also has DCC compression, and so that also reduced some of the pressure on memory bandwidth from the graphics engine. And between that and then a new efficiency arbiter that we put into the graphics engine that's also connected through to the memory controllers, we have much improvements on the request ordering to reduce DRAM page hazards. So how did we do? We grabbed, actually a few weeks ago, we grabbed and went through all the profiles of different games that we had run because they're great illustrations. And it turned out that Shadows of Mordor at 1080p actually exhibits quite a bit of memory activity compared to a lot of the other games. It was one of the more standout cases. And so what we did is we configured, in this case, the Raven device with the exact configuration of our previous generation 8 compute units. So this has Bristol Ridge and Raven Ridge on it. And so these are running, as you can see, I have frequency on the bottom axis and then frames per second on the left axis. So this really is showing the efficiency improvement and how it's translated to throughput of the graphics engine. And so we're really pleased with the results here. Okay, I did mention earlier that we included a new display engine. The display engine here, when we set out to design this, we had seen trends from, if you take it back to the time, most of the panels that were going in PCs were 13 by 7 panels, not even 1080p at that time. We also were seeing, movements to 4K, because this is 4 or 5 years ago now when we set this out. And so we said, let's revamp entirely the display engine. And so we set a target with this display engine to be able to do a 4K display at Vmin frequency, so lowest voltage of the process, and be able to do 4K throughput. So we ended up spending a fair bit of silicon on this. This has 4 pipes and flexibility in the pipes where we can combine pipes or we can use them as independent. So depending on what's plugged into the PC, you could have up to 4 displays, or we can do a much higher resolution at lower power with the combined pipes. So a nice attribute. So this display engine has 4 times the throughput as the previous generation. Likewise with the video codec engine, keeping up with all the codec improvements generationally, we did do improvements there, and this does 10-bit HEVC H.265 as well as VP9. Okay, a little bit about the power delivery. So power in this case, we also made a big change. In our previous generation, we had independent power supplies for the SoC, for graphics, and for CPU, so 3 primary rails coming in. In this generation, one of the problems we saw there was that we were having to over-provision those power supplies. In other words, each supply, the GPU and the CPU, had to be set for their maximum. And that meant that if you were working in different phases, that one of those supplies was working in a very inefficient place. So in this case, we decided to combine the rails into a single voltage rail and a single VDD in for shared by CPU and GPU. And so we did a first phase regulator there, where we have a variable voltage supply coming into the chip. Then inside the chip, we did a variation on a theme of, we had seen IVRs coming in play, but instead of doing the full voltage regulation on chip, we put individual low dropout regulators that would do the last stage of voltage regulators at each CPU core as well as in the graphics engine. So this allowed us much tighter fine-grained power delivery at wherever the power is being used in the chip, and a much tighter control of that to deal with, EDC type transients and so on. So how did we do on this? This is showing our previous generation Bristol Ridge with the 2 major rails for GPU and CPU compared to what we have in Raven Ridge with a single rail. Now granted, also remember that I was trying to push this chip into a smaller package too, and so that meant less pins. So now, since I have a single rail going into the chip, there's fewer device pins needed, or I'm getting more total current in and not having to make that compromise up. So we ended up with 36% less regulation hardware, out on the chip, and this gave us a 28% boost improvement. Also on the power management front, we did improve our state control of the processor, and so in this case you can see that we now have each core that can be controlled with its individual CC6. Since each one has its own regulator, we can individually power down each core. And then on the GPU side, we have now 2 major states that we can manage the GPU in. We have a very fast operating graphics off that we can trigger in and out of, and then we have a full up graphics power down, which takes out all the additional hardware, which can take out 99% of the hardware. So when we're in full GPU and graphics off, we can shut VDD off and then take out most of the power of the SoC. One area that we also worked on was in notebooks. We've seen much more attention in the past several years towards managing skin temps so that you don't have a lap warmer when you're really running a big compute job. So in this case, we included what we call STAM, or skin temperature aware power management. And so what happens in the device is we're monitoring the external ambient and we're comparing that to what we're doing on the chip, and we're exploiting that thermal excursion. So the white line is showing the previous generation where we really didn't have a way to exploit the full thermal excursion, which can take many seconds to even minutes. And so we were leaving a lot of performance on the table. In this case now, we have the ability to manage into that thermal excursion and essentially raise the overall performance across the workloads. So let's see how we did. I have a couple of examples here. So first of all, on graphics performance, I used 3D Mark Time Spy here and show the improvements that we made generationally. On the notebook side, we compare our previous generation Bristol Ridge as well as a couple competing devices, and you can see the class that those were in. And so we made a significant uplift in notebook graphics performance. And then even in the desktop, where we are starting to hit now the capabilities of the engine, we did even eke out even some more performance there, in that last batch of watts that are available. Most importantly was the frame rates of games. We really wanted to hit it out of the park on games and really be able to play great titles on this device. And so the key factor for that is frames per second. You got to get past 30 frames per second. In previous generations, we might have been in the teens and so on. It's just not playable. So now we went and took a sampling of a basket of common and popular games, and you can see across the board we did reach that, north of that 30 frames per second. Okay, so now I do a little bit of a report card. So we have been reporting out since 2014. We started an initiative in AMD called 25 by 20. What we wanted to do, our target and goal was to hit a 25% or 25x improvement in power efficiency by the year 2020. And so I'm showing here how we're doing. And so, as you can see, we're well on the way, making great progress towards this goal. This has not been easy. This is basically using a combination of compute performance combined with power and power management and idle power in a formulation that we've published. And so we're making great strides toward that goal. And even as we're rolling out machines through this year, you can see that we introduced Raven as a brand new device last year. With new systems that are coming out, we're seeing that curve continue up, or the efficiency even continue up even with Raven. Okay, so in conclusion, we have reached the true potential of we think with Raven and the APU. We have great data movement in the fabric and so on, and did improvements there. And last but not least, the advances in power management have really, and thermal management, have provided us with headroom for great visual throughput. So with that, thank you.
Thank you, Dan. Great talk. We have time for questions before we break for lunch. Please make your way to the microphones.
I'm Jason Wang from Sony Interactive Entertainment. I just would like you to talk more about the term like the coherent master, coherent sleeve, and non-coherent master.
I can hear.
Could you just repeat the question one more time, please?
Oh, talk about the terms about the coherent master, coherent slave, and non-coherent master.
Right. So coherent master, coherent slave, and non-coherent master. Right, what's going on there is essentially the coherent masters are participating in the coherence protocol for shared data within their cache subsystems, and then talking to main memory, and the slave itself is the memory controllers. That's our point of global visibility for coherent traffic, so all coherent traffic will go through that if it's tagged as coherent, and then will be broadcast out to take care of any memory coherency cleanup and bringing cache lines. The non-coherent devices, such as I/O and so on, don't participate in that coherent traffic.
I see. So when we use non-coherent devices, we have to make sure the cache is flushed. Is that a hardware automatically flush the cache, or?
Correct. Anything that's considered part of the non-coherent relies on software coherency. Expected it usually won't have caches as part of it, and so software semaphores have to take care of any flushing that would have needed for those devices.
Thank you.
Sure.
Right. Jeff from the Citadel again. This might have just been answered through the last question, but are the display controllers actually coherent memory consumers, or are they just spooling things out with some sort of DMA equivalent access?
One more time, sorry.
So the display controllers, are they actually pulling things off of the memory controller with coherent memory requests, or?
Yeah, no. So usually the frame buffer will be in considered non-coherent memory. It could be pulling, but usually that would have been built in non-coherent memory space, and so therefore doesn't become a part of the bottleneck. You know, the coherent traffic dealing with that. Yeah.
Okay, thank you.
Yep.
Maybe a high-level question for me, Dan. So Moore's law is very painful these days, yet you guys can keep going on your projectile on forward. Main insights, key lessons that you guys learned on how to stay on course for performance and power?
Yeah, it's a good question. Definitely, we are seeing improvements. We're really looking forward to 7 nanometer. It's another improvement, and even beyond. I think some of our biggest challenges today is turning out to be I/O scaling. As a matter of fact, so we are seeing the transistor scaling. We're seeing improvements in a lot more that we can play with going forward. But if we start looking at the I/O boundedness that we're running into, especially memory throughput. And trying to improve that, as well as just the general, becoming I/O bound in the SoCs. I think that's probably one of our bigger challenges coming. And then last but not least, thermal management. Again, continues to be very much a challenge. Dealing with, in this case, thermal density. Again, trying to tune every last bit, out of the device.
Great. Thank you, Dan.